Okay, so what I want to talk about is the following problem. This here is the first iteration of a four-corner Cantor set. Basically what you do is the following. You start with a square in the plane. You subdivide it into 16 identical little squares, and you choose 4 of them at the 4 corners of the square. And then you iterate that to get a Cantor set. Inside each of the 4 squares that you have chosen here, you put a little copy of the big set I just constructed, and then you keep going. You get a, oh, oops. Switch notes here. You get a set which I'm going to call E infinity. That's the intersection of En, where En is going to be the nth iteration. The intersection is from okay. The intersection is from n equal 1 to infinity. It's not terribly hard to prove that the dimension of E infinity is 1, the Hausdorff dimension. Also, E infinity is completely unrectifiable. And one of the consequences of that is as follows. Suppose that you look at one-dimensional projections of E infinity. Here's one example. Theta is going to be the angle at which the projection is taken. So that's the angle here. And then pi theta is going to be the projection of the set in that direction. The 2 line segments that I highlighted here are going to be pi theta of E1 because this is the first iteration. Now, one of the consequences of the fact that I mentioned on the previous slide is that pi theta of the Cantor set E infinity you get in the limit has one-dimensional measure 0 for almost all theta. And I'm going to come back to that statement a little bit later. A consequence of that is that if you look at pi theta of En, the projections of the finite iterations of the set, then the length of that is going to go to 0, again for almost all theta. That's just a trivial consequence of that. In fact, if you also refer to the dominated convergence theorem, you can say a little bit more. Namely, that if you integrate this quantity from 0 to pi in theta, you get that this is going to go to 0 as n goes to infinity. The hard question is how fast? And that's still open. There are bounds from above and below, which I'm going to state in a moment, but the optimal rate of decay is not known. Let me call this Ln. And here what's known about it for the time being. We oops, that was here. There's a lower bound a very general lower bound due to Matila. I think that's from 1990, which says that Ln is bounded from below by a constant over n. That, in fact, applies in a much more general setting. If instead of a four-corner Cantor set, you take a more general Cantor set where you subdivide the square into some other number of parts, and then you choose some of them, and then you iterate that, and you do it so that the set you get in the limit has dimension 1, then Matila's bound is still going to be valid in that setting. In the specific case of the four-corner set, there's a better bound due to Bateman and Volberg. And that was last year, 2008. They proved that Ln is greater than C log n over n. This here was more general. And this is for the four-corner set specifically. Though actually there is a generalization that's possible, and I'm going to mention that in a moment. The question that I was working on was the upper bound. Now, for a long time, pretty much nothing was known in terms of quantitative bounds. The first such bound was proved by Perez and Solomiak. That was around 2002. They proved that Ln is bounded from above by a constant times e to the minus c log star n, where log star of n is the number of times that you have to take the logarithm of n until you get to 1. So that's not anywhere close to what's expected, which is somewhere in that area. A better bound was proved by Nazarov-Perez-Volberg last year. They proved that Ln is bounded from above by a constant times times the negative power of n. Specifically, they proved that you can take n to the 1/6 minus epsilon here for any positive epsilon. They claim that if you work on it a little bit harder, you may be able to improve the exponent to 1/4 minus epsilon. To go beyond that, you would need new techniques. Basically, they wouldn't know how to go about doing that. The Perez-Solomiak bound that I just mentioned applies in a more general setting. You can take a more general class of self-similar Cantor sets, and their proof still works. But the proof of Nazarov-Perez-Volberg works only for the four-corner set. And I'll talk later about why it's specific to that setting. The result that I want to talk about is joined with my student Kalan Jai. It says that Ln is bounded by a constant times a negative power of n. Oops. See, how do you erase it?
When you push the button on the pen, you circle what you want to erase. Push the button on the pen.
Okay. Guess it worked. Okay, so we have an n to some power gamma. Gamma is positive. For more general sets En. En is going to be a self-similar Cantor set obeying two conditions. One is that it's a product Cantor set. The other condition is that there is a direction theta in which the projection has positive measure. Oops, sorry. Pi theta. Just to go back for a moment to the four-corner Cantor set, you can see that there's a direction pi theta of E infinity has positive measure, and that's going to be this direction here. If you just look at the first iteration, you can see that the first iteration of the set gets projected on an uninterrupted line segment from here to there. And then if you continue iterating the construction, if you, for instance, look at what this first square here gets projected, you just make this picture a little bit smaller, rescale it, and you see that the projection of this little square is again going to produce the line segment from here to there, and the same for each of the remaining squares. And then you can iterate that as many times as you like. You get that the actual one-dimensional Cantor set you get in the limit also gets projected to an uninterrupted line segment. So in particular, that has positive measure. This is not the only case in which that sort of thing can happen. It can actually happen in much more complicated ways, and that's part of the problem here. But anyway, that's the condition that we need. We actually expect that some sort of a condition like that should actually make a difference in how the projections are going to behave. If you go back here to the lower bounds, and specifically if you look at the lower bound of Bateman and Volberg here that I mentioned, their proof uses specifically the fact that I just mentioned, that the four-corner Cantor set gets projected to an uninterrupted line segment if you choose your direction the right way. That's important in the proof. We think that the same argument extends to the case that I just mentioned, when there's a direction in which the projection has positive measure. But we also think that that condition is essential for having an improved bound like that. We expect that if there is no such direction, then Mathila's bound should be optimal. And in fact, in the same paper here, Perez and Salomiak had a construction of random Cantor sets of dimension 1, for which Mathila's bound is in fact optimal. So basically we expect that the case when there is no direction in which you have this estimate, that case should just be treated by different methods. It's probably basically a different kind of a story going on. The condition that our set should be a product set is a little bit annoying because we don't expect that that should be necessary. And in fact, there's a bit of a hope that maybe we can get rid of that. There is a very recent result of Volberg and his student Matthew Boltz, if I remember the name correctly. They proved a similar estimate for the self-similar triangle. They use, again, methods similar to those of Nazarov-Perez and Volberg, except that the triangle is obviously not a product set. So we expect that we may be able to combine what we do here with what they do and possibly get rid of the assumption that the set has to be a product set. Okay, I'm going to try to say a little bit about how that sort of thing gets proved. I'm going to start by explaining a little bit about the proof of Nazarov-Perez and Volberg, and then I'm going to say how we modify that to get our result. Okay, so here's a very rough sketch of the paper by Nazarov-Perez and Volberg. I can't really begin to tell you how good that paper is. It has a lot of great ideas, and I can't really do a lot of justice to it here in a few minutes. We start by defining a counting function which I'm going to call fn of x, or more precisely, it's going to be fn of theta and of x, because it depends both on x and on the angle of the projection. Basically, what that function does is, for a given point, say x here, you go back in the direction perpendicular to theta, and you count the number of squares that get projected to that point for the end projection. In this case here, for the x as indicated, f1 of x would be 2, because you get 2 squares projected on it. For this point here, for instance, it would be 0. Okay, so that's our f. And then there's an estimate that Nazarov-Perez and Volberg prove. Basically, it says that the L2 norm of Fn is small for most values of data. I'm going to write that out more precisely in a minute. The reason why this is supposed to be good is that, take a look at this picture here. We want to prove an estimate from above on the length of the projections pi theta of En. Now, how is it going to be possible for that projection to be large? The only way that that can happen is if you have a lot of squares whose projections don't intersect. So they're going to be disjoint. That means that most points here are going to have low multiplicity. There is not going to be a lot of squares projected to them. And that basically converts to a small L2 norm of the counting function for the given direction. So if the L2 norm is large for most directions, you get an estimate here from above. And there is indeed a combinatorial argument which converts these L2 estimates to estimates on Ln. The combinatorial argument is very general. You can do it for large classes of self-similar sets. The part that's specific to the four-corner set is the main estimate, the estimate on the L2 norm of Fn. The proof of the main estimate uses harmonic analysis. Basically, what you want to do is compute the Fourier transform of the counting function, and then estimate the L2 norm of that. The main part of doing that is you want to estimate the following quantity from below. Write the integral from 4 to the n to 4 to the n plus n of Pn of y squared dy, where m is some number that they fix in their paper. And Pn is an explicit trigonometric polynomial. Pn of y is the product from k equals 0 to n of cosine 4 to the k y cosine of 4 to the k times ty. And this is specific to the four-corner set. I think you can see why. I don't want to explain how exactly the problem gets reduced to that unless you want my talk to extend to another hour. But anyway, you calculate the Fourier transform of Fn. You do a couple of other reductions. There's a pigeonholing. There's a decay estimate and such, and you end up having to estimate this. Now, what they do at this point is pretty clever. They split this into a product from k equal 1 to m times the product from k equal to m plus 1 to n. This is going to be the first part, and this is going to be the second part. And then they do different things for those two different parts. This is going to be the high frequency part, and this is the low frequency part. For the low frequency, for the high frequency part, that they can prove that this is good. And that the integral of the square of that is large. That uses something they call Salem's trick. It actually took me a while just to understand why that estimate is not supposed to be trivial. And then it took me, again, some time to understand exactly what they're doing. So again, I can't really go into details here given the limited time, but I'm just going to ask you to believe me that this is non-trivial. And anyway, it's quite complicated, actually. And anyway, this part generalizes fairly easily to the setting that we want to work with. The part that's difficult to generalize is the low frequency part. Basically, the idea is the following. By the first part here, if you only had to estimate a product like this with the low frequency part here deleted, that would be an easier task. You would be able to do that. And you would actually have a much better estimate than you end up having. So what you want to prove is that when you put in this additional low frequency part, then that's not going to screw things up too much. Specifically, you want to prove that the integral of the high frequency part doesn't concentrate on the set where this here is small. I guess I gotta work on this a little bit longer. We want to prove that the integral of 2 does not concentrate on the set of those x's where 1 is small. And if we want to do that, we need to know more about the set where 1 is small. And that's where it's important to have an explicit form for that. You basically end up using an explicit trig identity to estimate that. And it turns out that you can evaluate the low frequency part pretty much in closed form. And that's really specific to the four-corner set. There's just a trigonometric identity to evaluate the product of cosines. Okay, so in our paper, the main task is to extend the estimate on the first part. Specifically, we want to know the set of small values of the expression that in our paper corresponds to 1. And basically what we end up using is a tiling argument, which I'm going to explain now. What we're looking at is, let's see, more general sets where you subdivide the square into some number of little squares, then you pick a few of them. Oops, that was supposed to be a square. Okay, you get the idea. Actually, in our setting, that's supposed to be a product set, so they should be arranged more like this. Oops, I'm getting too much of it. And anyway, the point here is that I can label these things as follows. If my square is subdivided into k parts, I'm going to label the endpoints by integers, 1, 2, 3, 4, up to k minus 1 here, and same here. And my product set is going to correspond to two sets, A and B, subsets of integers from 0 to k minus 1. And let's see. I'm first going to explain how things work in an easier case. Suppose that there is a direction theta such that the projection of E infinity in that direction is a line segment. So that would be a case like what we have seen here with the four-corner set. That's just a special case of what we're doing. What this means in terms of the sets A and B is that A plus B, the sum set, is, well, but basically it looks like the set of, okay, I cannot quite say that it's the set of all integers from 0 to k minus 1, but I can do the following. I can say that there are integers k, l, and r, such that ka plus lb is r, is 0, r, 2r, k minus 1 times r. Basically, that's what the that's what this condition ends up amounting to. Now, this can be rewritten in terms of generating functions. A generating function of A is going to be the polynomial A of x equal to the sum over A in A of x to the A, and likewise for B. And then the tiling condition from the last screen can be rewritten as follows. A of x to the k times b of x to the l is equal to 1 plus x to the r plus x to the 2r plus x to the k minus 1 times r. And that's something that can be evaluated in a closed form. That's 1 minus x to the k times r over 1 minus x to the r. And that's going to be our substitute for the trig identity that Nazarov-Perez-Volberg used. And that's basically what makes the proof work. Now, this was a special case. In general, it's not necessarily true that if the projection has positive measure, then you have to have that case. It can happen in more complicated ways. You don't have to have an uninterrupted line interval. But instead, what you need to refer to is the work of Cantor and Lagaria-Sweng. Back from 1996. If you assume that the projection of a set has positive measure, then first of all, the tangent of theta is rational. And moreover, there is a tiling of the integers, which is associated with the set E infinity. And if you work on it a little bit harder, then you can also say that there is a tiling associated with finite iterations of the set. That's En here. And then if you again do some more work, then you can use that as an acceptable substitute for those trig identities and other such. And that's how you can make the proof work. Okay, I think I'll better stop before that timer starts beeping on me. Thank you.
Does anyone have a question?
I'm trying to understand the dichotomy you want to make between sets where Favard-Volberg works and sets like Modula has. So suppose that instead of looking at the L1 norm of the projection of the N, I look at the L infinity norm. So if I have a projection that has positive measure, then I get constant. And if I have a random set, then I should get something like 1 over n. Do you believe there's any restriction on the order of decay that you can get?
I don't know really.
I think that if you were able to get a decay which is slower than 1 over log n, you should, or maybe 1 over square root log n, you should still be able to get something from Favard-Volberg. So I don't know if such decay is possible.
You mean if...
I mean,
okay, so you're not...
measure that you have.
Okay, so instead of the... see, you're just fixing a direction, and then you're looking at the length of the projection in that direction, and you're looking at how that decays in n.
Well, I'm souping over directions, but okay, we can fix the direction.
Okay, so the L infinity norm refers to the maximum length of the projection.
Right.
Yeah, I don't... this is something that we just started looking at recently. So I think the case of positive measure works. I'm not sure about the case of slow decay. This certainly would be something to look at. On the other hand, I don't know whether that case is actually.
That was what I was
Well, I don't know whether that can even happen.
Yes.
So,
That was my question.
okay.
What kind of dynamic
I can write that out for you. They use that the product from L equals 0 to 2m of cosine 2 to the L minus 1, no, L u is sine of. Mm-hmm. I think this should be 1 and this should be L minus 1. There you go. Okay, so that's if you read it the right way, then that corresponds exactly to that tiling identity with polynomials that I wrote out earlier. If you convert x to or u to a complex exponential.
Any other questions?
Is there an discrepancy for the
That's actually the question that Volberg and his student are working on. So yeah, there is a question. Kenyon's paper is actually about the Sierpinski gasket, the triangle, right? So you first of all modify it so it has dimension 1. And then that's the problem that Canyon worked on. And that's also the problem that Volberg and his student Boltz are writing a paper about right now. Okay, that I'm not sure about. You need your set to have one-dimensional measure. You need your set to have one dimension to begin with. So what's the gasket that?
The gasket is the same construction as in the gasket, but then starting from a square. Then you start to remove like in the gasket.
Okay, I'm not sure which one you're referring to. You could.